Chapter 6 is exponential and logarithmic functions, or log for short. Section 6.1 starts off with a little bit of review about exponential growth and decay functions. So example 1 says graph the following functions. The first one, part A, is y equals 3 to the x power. So we're going to graph it with a table. For our x values, we're just going to use -1, 0, and 1. So if I substitute in -1 into y equals 3 to the x power, that's going to be 3 to the -1 power. And then properties of negative exponents tell me I need to take the reciprocal of the base. So 3 to the -1 is 1/3. And then when I substitute in x equals 0, I get 3 to the 0. Anything raised to the 0 power is just 1. So not like the exponent becomes 1, but the whole thing just becomes 1. So 3 to the 0 power is 1. And then when I substitute in 1, I get 3 to the first power, or just 3. So then we can start to graph these. So if we scale our x and y axis, I have a point at -1, 1/3, so left one up about 1/3, and just do your best to estimate it. 0, 1, and then 1, 3. So right one up 3. And then we can connect our points, and you can see that the graph increases really quickly. And then for b, f of x equals 1/3 to the x power. So we're going to use the same values for x on our table. We're going to use -1, 0, and 1. We can use that for any exponential function. And an exponential function is just like a number raised to a variable exponent. So like we have an x as our exponent here and an x as our exponent here. So that makes these exponential functions. So if I input -1 for x, this becomes 1/3 to the -1, and then I know if I have a negative exponent, I need to take the reciprocal of the base. Since the base is 1/3, the reciprocal of that is 3/1, or just 3. So 1/3 to the -1 power becomes just +3 to the first, or just 3. And then when I input 0 for x, 1/3 to the 0 power, anything to the 0 power, is just 1. And when I input 1 for x, this becomes 1/3 to the first power, or just 1/3. And now we can graph it. So I have a point at -1, 3. So from the origin, left one up 3, 0, 1, and 1, 1/3. So right one up about 1/3. So if we take a look at these two graphs, these two functions and two graphs. So the first one, y equals 3 to the x. So I had a whole number base, or I had a base that was greater than 1, or 1 or greater than 1. So I had a function that was increasing. So we always talk when we're thinking about increasing, we look to the right. So as it goes to the right, it's increasing. And then for b, I had a function where the base was a fraction. It was between 0 and 1. So if I have a fractional base, then my graph is going to, or more really between 0 and 1, my graph is going to be decreasing to the left. So that's kind of the difference between exponential growth and decay, is just what the base number is. So if we look at example 2, it says tell whether the functions represent exponential growth or decay. So the big thing is, if I have a base, so like 3 is my base, 1/3 is my base. If I have a base that's greater than 1, it's going to be growth. If I have a base that is between 0 and 1, it's going to be decay. So if I look at a, it's y equals 4 to the x power. So 4 is my base, that's greater than 1, so this is growth. If I look at b, it's y equals 3 times 1/2 to the x. The base is just whatever is being raised to the x power, so the 3 isn't the base, the 1/2 is the base. Because we wouldn't like multiply these two together and then raise them to the x power, we would raise the 1/2 to the x power and then multiply by 3, so the 1/2 alone is the base, and since 1/2 is between 0 and 1, this is a decay function. And then for c, f of x equals 2/3 to the x power. So 2/3 is my base. That's between 0 and 1, so that's decay. For d, g of x equals 5/4 to the x power. 5/4 is greater than 1. So even though it's a fraction, it's still greater than 1, so this is growth. And then e, k of x equals 0.3 times 1.5 to the x power. So here the 1.5 is being raised to the x, so that's my base, and 1.5 is greater than 1, so this is growth. And then the reason that an exponential function with a base greater than 1 makes it grow versus a base that is between 0 and 1 makes it decay is because think about if you have a fraction and you start to multiply it again together over and over again. So like if I do 1/2 squared, I would square both and I would get 1/4. So that makes it smaller. So raising a fraction that's between 0 and 1, or a decimal even, to an exponent actually gives you a smaller value. 1/4 is smaller than 1/2. Or if I would have done 1/2 to the 4th power, I would raise them both to the 4th, so I would get 1/16. That's definitely smaller than 1/2. So raising a number between 0 and 1 to an exponent is just going to make that number get smaller, so that's creating the decay. And then I would take a second to copy down these definitions. And exponential growth is when a real life quantity increases by a fixed percentage each time period. And then our formula for that is y equals a times 1 plus r to the t. And then exponential decay when a real life quantity decreases by a fixed percentage each time period. And our formula is y equals a times 1 minus r to the t. And then basically r is just the rate that it's changing. So if it's increasing, that's why we're adding r. If it's decreasing, that's why we're subtracting r. So for example 3, it says in 2000, the population of a city was about 1.04 million. During the next 14 years, the population increased by about 2.05% each year. Part A says write an equation to model the population t years after 2000. So since it's saying that the population is increasing, to write an equation that models it, we need to use the exponential growth formula. So we'll start with y equals a times 1 plus r to the t. And then we need to figure out what values that we can substitute in. So it says to write an equation to model the population t years. So that's for any amount of years. So t is going to stay in this formula. And then a is the initial amount that you're starting with. So since in 2000 the population was 1.04 million, 1.04 is going to be our a. And you can just leave it as 1.04. And then once we substitute in an actual t value to get, like for example b in 2008, we'll just add million after. And then the rate that it's changing, it's increasing by about 2.05% each year. So if it's increasing by about 2.05% each year, that's going to be our r, but we need to change it to decimal form instead of percentage. So we need to move the decimal 2 places to the left. So that'd be 0.0205. So we'll input 1.04 for a, 0.0205 for r. So y equals for a 1.04 times 1 plus 0.0205 times t. And then we can just simplify it by adding 1 plus that decimal. So y equals 1.04 times 1.0205 to the t power. So that's our equation that models the population t years after 2000. And then for part B, estimate the city's population in 2008. So since the t is representing the years after 2000 and we're trying to find the population 2008, we would need to find the population when t equals 8. So we're just inputting 8 in for t and then simplifying it. So y equals 1.04 times 1.0205 to the 8th power. So we have to raise 1.0205 to the 8th power first and then multiply it by 1.04. So about 1.762 or 626, and then multiply by 1.04. So we get about 1.22. And then because that 1.04 was in millions, the 1.22 will be in millions as well. So for part C, this is something that I would usually do on Desmos. So I'm gonna, when we're in class, I'll go over it on Desmos as well. But obviously for the video, it's kind of difficult. So we'll go over this part in class. And then eventually in this chapter, this is gonna be something that we're gonna be able to solve for. So estimate the year when the city's population was 1.3 million. What we would do to estimate it right now is we would input this equation into Desmos. And then we would just along the line, because it's exponential growth, along the line find when the height of the point or the y coordinate of the point is 1.3, and then figure out what the x coordinate of that point is. That'll be our t value. But I'll show you guys in class, and then we'll move on to example 4. So example 4, the amount y in grams of the radioactive isotope barium-140 remaining after t days is y equals a times 0.5 raised to the t over 13, where a is the initial amount in grams. What percentage of the barium-140 decays each day? So we'll start just by rewriting the equation that we're given. So y equals a times 0.5 to the t over 13. So we're basically trying to find the decay rate. So it says what percentage of barium-140 decays each day. So we're trying to find the decay rate. So in order to do that, we're gonna have to rewrite the equation or figure out a way to rewrite the equation so that it looks more like the exponential decay formula. So the first thing that we can do is the exponential decay formula just has to the t power. This one has to the t over 13 power. So we can use the properties of exponents in reversed to break apart that t to the 13th power. So we're going to rewrite this as a times 0.5 to the 1/13. And then that 0.5 to the 1/13 is going to be raised to the t power. So we can separate this because like 1/13 times t is t to the 13th. So we're using the power property in reverse, whereas like if I was on this step and I was trying to simplify, I have a power raised to a power, so I would multiply these exponents to simplify it. So 1/13 times t would get me back to t over 13. And then now I can go ahead and I can simplify 0.5 to the 1/13 power. So 0.5 to the 1/13 power. Make sure if you have like a rational exponent that you put it in parentheses just to be safe. So 0.5 raised to the 1/13 is about 0.9481. So we're going to rewrite this as a times 0.5 to the 1/13 was 0.948, and then 1 if we round up from that 7 to the t power. So we're not changing any values here or anything like that. We just simplified 0.5 to the 1/13. And then now we're getting really close to this looking like the exponential decay formula where we can see what r is. So this 0.9481 is just this 1 minus r simplified. So if I want to find what r is, I need to take 1 and subtract 1.9481. And I get 0.0519. So that's going to be r, because I can rewrite 0.9481 as 1 minus 0.0519 and then to the t power. So all I did right here is I rewrote it as 1 minus something. I didn't change the quantity of what was inside the parentheses. You find this number by subtracting 1 minus this, because that means that these two added together will get you back to 1. And you can always double check it to make sure like you're not actually changing the value. So 1 minus 0.0519 gets me back to 0.9481. And then now this looks exactly like the exponential decay formula. So y equals a times 1 minus r to the t, and we can see what r is now. So r is approximately 0.0519. Or if we put it back in decimal form, we have to move the decimal twice to the right. So it's about 5.19%. So example 5, your grandma gives you $1,000 when you're born. Your parents put money in a savings account that pays 5% each year. How much money will we have when you're 18? So this is now talking about exponential growth because it's collecting interest each year. And then my exponential growth formula is y equals a times 1 plus r to the t. So a is our initial amount. That's how much we start with. R is the rate that it's growing, and t is the amount of time that's going by. So your grandma initially gives you $1,000. So a is $1,000, and then your savings account is paying 5% each year. So that's telling you R. And then it's asking you how much money you'll have when you're 18. So if it starts when you're born, that 18 is going to tell you your t. So t is going to be 18. So our growth formula, like I said, is y equals a times 1 plus r to the t. So we figured out what a, r, and t are. So a is 1,000. That's how much you start with. Times 1 plus r. I need to change this to a decimal though. So 5% is 0.05. If we move the decimal place 1, 2 to the left. So this is going to be 1 plus 0.05. And then to the t power, so to the 18th power. And then we can add the numbers inside of the parentheses and then use our calculator to figure out the rest. So y equals 1,000 times 1 plus 0.05, so 1.05 to the 18th power. We need to raise 1.05 to the 18th power first. So about 2.4 and change, and then multiply that by 1,000. So $2,406.62 or about. So if you're given $1,000 and you had a savings account that collected 5% interest each year, or pays 5% interest each year, once you turn 18, you'll have over $2,000. And then there's something that's also called compound interest. So compound interest means that something is collecting the interest is compounding, so it's building on top of each other and continuing to grow. It grows at a faster rate. So our compound interest formula is a equals p times 1 plus r over n to the nt. So for example 6, you deposit $8,600 into an account that pays 1.32 annual interest or percent annual interest. Find the balance after 5 years when the interest is compounded quarterly. So if I start with my compound interest formula, a equals p, which this changes a little bit between the exponential growth and this formula. So p, since compound interest is specifically talking about money as growth or decay or whatever it is that we're dealing with, p stands for principal, which is still just like the original amount. So my p would be 8,600. My R is 1.32%. And then we're finding the balance after 5 years, so T is 5. And the interest is compounded quarterly. So in this case, N is how many times it's compounding each year. So if it's compounding quarterly, then that's compounding 4 times each year. Quarterly is just 4 times a year, every 3 months. So N is 4. So we can plug P, R, T, and N into this formula and simplify. So P was 8,600 times 1 plus R, which was 1.32 as a percent. So if I change it to a decimal, I have to move the decimal twice to the left, so 0.0132. So 1 plus 0.0132 over N, which was 4, raised to the N times T, so raised to the 4 times 5. And then we can start simplifying it. So we'll leave the 8,600 out front for now. If we simplify inside the parentheses, 0.0132 divided by 4 is 0.0033, and then plus 1 gets us to 1.0033. And then raised to the 4 times 5, so raised to the 20th. And then from here, we can raise 1.0033 to the 20th power. So about 1.068. And then I can go ahead and I can just multiply that by the 8,600. I'm going to write that middle step just in case anybody's a little bit behind. But we're multiplying 8,600 by about 1.0681. If you can just leave it in your calculator, that's better, so you're not like rounding it too early. But we'll multiply this number by 8,600. So we end up with A is approximately, since it's in money, we'll round it to 2 decimal places, so $9,185.75. So for 6.2 is all about the natural base e, which is just a specific base that you can have for exponential functions. So recall the compound interest formula, which we just talked about. It was a equals p raised to the 1 plus r over n to the nt. So for this table, we're going to fill out different variations of how much it's compounding. So it compounds quarterly, compounds monthly, compounds weekly, compounds daily. So we're going to start with $1,000, so P equals 1,000. The rate is 6% and T is 10 years. And we're just going to see how compounding at different amounts changes the actual value that you end up getting. So if my rate is 6%, that means that R is actually going to be 0.06 at the decimal if we just move the decimal place twice to the left. And then if we're compounding quarterly, we talked about that makes N equal 4. If I'm compounding monthly, again, remember N is how much you're compounding each year. So if I'm compounding monthly, there's 12 months in a year. So it'd be N equals 12. If I'm compounding weekly, there's 52 weeks in a year. So that'd be N equals 52. And if I'm compounding daily, 365 days in a year. So that would be N equals 365. So it's basically the same problem each time. It's just the only thing that's changing is N, obviously. Our P, R, and T will stay the same the whole time. We'll just notice how you're getting different amount of money at the end of each one. So A equals P, which was 1,000, times 1 plus R, so 0.06, over N. In this case, N is 4. To the N times T, so 4 times 10. So if you want to do more work on a scratch paper, I'm going to pretty much do all of it in a calculator just because I don't have a ton of space. So if we start inside the parentheses and simplify, 0.06 divided by 4 is 0.015 plus 1. Oops, no, not what I wanted to do. Sorry. So 1.015. And then I'm raising that to the 4 times 10 power. So if I raise that to the 40th power, it becomes 1.8 something. And then I have to multiply it by the 1,000. So about 1,814.02. And then we'll do the same thing now for when it compounds monthly. So A equals 1,000 again. The P is the same. The amount we start with is the same. And then times 1 plus R over N. So R was 0.06 over, in this case, N is 12. And then a raised to the N times T. So 12 times 10. So 0.06 divided by 12. So 0.005 plus 1. And then that's being raised to the 12 times 10. So raised to the 1/20th. And then I need to multiply that by 1,000. So about 1,819.40. So when it compounds monthly, you make a little bit more than when it compounds quarterly. So now we'll do weekly. So A equals 1,000 times 1 plus, the rate is the same, it's still 0.06, over N, which is now 52. Raised to the N times T, so 52 times 10. And then we'll simplify the inside the parentheses first, so 0.06 divided by 52. And then plus 1. And then raised to the 52 times 10 is 520. And then we'll multiply it by 1,000. So about 1,821.49. Then we make a little bit more weekly if we compound weekly versus monthly, and then we'll check daily now. So A equals 1,000, we're still starting with the same amount, times 1 plus R over N, so R is the same, 0.06, over N, which in this case is 365, raised to the 365 times 10. So, or times T, so 10, and then just to save space, I'm just going to write it as 3,650. So when we multiply 365 by 10, we're just going to add a 0 at the end. So 0.06 divided by 365, and then plus 1, and then times 1,000. Oh, I did that backwards, sorry. I forgot the step. Sorry, 0.06 divided by 365, and then plus 1, and then we need to raise it to the 3,650. So raise to the 3,650, and then times 1,000. So 1,822 and about 3 cents. So you can see it doesn't make like a ton of difference, like just from compounding quarterly to compounding daily, it was about what, $8 difference over the span of 10 years. But obviously, like the more money you have as well, the bigger difference it's going to make. The longer time that you give it, the more difference it's going to make, and so on. Okay, so the natural base E. So as x increases, 1 plus 1 over x approaches this number E. And E is kind of like pi, where it's like an actual number. It's like 2.714 forever. So 2.718 and this is an approximation as well, so it doesn't even end here. It's an irrational number that goes on forever, just like pi. We usually not simplify it, but we usually cut it off at 2.71 or sometimes 2.7. And then there's a formula for interest compounding continuously. So not even just like quarterly, monthly, weekly, or daily, continuously. And that's A equals PE to the RT. So P is the same, where that's like your initial amount, the principal. R is the same rate, T is the same time, and E is an actual number. So we're not going to substitute anything in for E. There's actually an E function on your calculator. So compound interest, let P equal 1,000, R equals 6%, T equals 10. So we're using the same kind of information as we did up on the table, and we'll just see what happens when we compound it continuously. So find the amount after 10 years if it's compounded continuously versus up here we only compounded quarterly, monthly, weekly, and daily. So A equals P E to the RT. So in this case, P is 1,000, R is 6%, T is 10. And E, like I said, is a number, so we're not actually substituting anything in for E. So if P is 1,000, it would be 1,000 times E raised to the R, which 6% is 0.06, and then times T, which is 10. And then if I want, I can simplify like 0.06 times 10. That just becomes just 0.6. So 1,000 times E raised to the 0.6 power. So I know everybody's calculator is different, and if you're ever having a hard time like figuring out how to do it on yours, you're welcome to like send me a picture of it. So on mine up here, like above the ln, there's an E to the x power. So if I want to use that, I'll simplify E to the 6th power first and then multiply by 1,000. So I'm gonna hit second, the ln button, and that'll bring up the E raised to the, and I'm gonna raise it to the 0.6 power. Just hit enter. So about 1.822, and then times 1,000. So about $1,822.12. You can see it doesn't make like a huge difference from when it's compounded daily. But like I said, like the more money you invest, the more difference it makes. The longer you leave it, the more difference it makes and stuff like that. And then for example 1, you deposit $4,250 into an account that earns 5% annual interest compounded continuously. What's the balance in the account after 10 years? So if it's compounded continuously, this is the formula that I'm using. So this like 6.1 and 6.2 is a lot of formulas. Like on your homework, I would write the growth, the decay formula, the compound interest formula that was up here, and then the continuously compounded interest formula down here. I would write them all just so it's like easy to get to. So if it's compounding continuously, I'm going to use A equals P E to the RT. So if I deposit $4,250, that's my original amount, my principal. So P is $4,250 into an account that earns 5%. So that's my R. But I'm going to change it to a decimal. So I have to move this decimal place 1, 2. So that's 0.05. And then if we want to find out what the balance in the account is after 10 years, that's my T. So A equals P, which was 4,250 times E raised to the R times T, so 0.05 times 10. 0.05 times 10 just becomes 0.5. So this becomes 4,250 times E raised to the 0.5 power. And then now we can simplify it. So same thing before, I'll hit second and then ln, at least on this calculator. And then E is being raised to the 0.5 power. And then I'm going to multiply that by 4,250. So A is approximately $7,007.07. And then the last few examples are just specifically working with like e and simplifying exponents. With e, it works the same thing as simplifying like exponents over any base, so all the properties work. And then we'll even do some graphs for you as well. So example 2, simplify. I have e to the second power times e to the ninth. So when we have the same base on our, or under our exponents, in this case e, and we're multiplying like we are right here, we add those exponents. So e squared times e to the ninth would become e to the 2 plus 9, so e to the 11th. And that makes sense because you have 2 e's multiplied together, and then you multiply in 9 more, so altogether you have 11 e's multiplied together. So e to the 11th. And then for 25, e to the 13th over 5 e to the 12th. So I can reduce the 25 and the 5. I can divide them both by 5. So the 5 would become a 1, and the 25 would become a 5. And then the e to the 13th over the e to the 12th, I have the same base now, e, and I'm dividing. So I'm going to subtract those exponents. So 13 minus 12 is 1. So I'm left with e to the first power, or you can think of it as like these 12 e's cancel out 12 out of the 13. So I'm just left with an e to the first power in the numerator. And then all together in the numerator, I'm left with 5 times e, so 5e. And then for c, 2e to the negative 3x to the 5th power. So I have a couple different factors in here that are both being raised to the 5th. So because each of these factors are being raised to the 5th power can go to both of them. So I can first simplify this to 2 to the 5th, and then e to the negative 3x to the 5th. I'm raising a power to a power, so I multiply those exponents. So that becomes e to the negative 3x times 5 is negative 15x. So 2 to the 5th, e to the negative 15x. And then 2 to the 5th, I can simplify, that's 32. And then because I have a negative exponent, I need to simplify that as well. So because I have a negative exponent, I have to take the reciprocal of the base. Or because it's in the numerator, it'll go to the denominator. So we'll create a denominator. So the 2 to the 5th is staying in the numerator because it's not being raised to a negative exponent. 2 to the 5th is 32. And then e to the negative 15x, to make it into e to the positive 15x, I have to move it to the denominator. That would become e to the positive 15x. And then if we want to graph these next two functions, for example 3, it says graph f of x equals 2.5 e to the x and y equals e to the negative 0.2x. We'll graph these using a table as well. And it's the same thing as with 6.1. We can just use for our x values -1, 0, and 1. So for x, I'll pick -1, 0, and 1. And this is just a calculator problem. So like I don't need to necessarily simplify e to an exponent in my head. I have that function on the calculator. So I'm going to raise e to the power of x and then multiply by 2.5. So first I'm going to raise e to the negative first power. So second ln, e raised to the -1 is going in for x. Evaluate that, and then it's being multiplied by 2.5. So it's about 0.92. And then if I raise anything, if I input x equals 0, so if I raise anything to the 0 power, the whole thing becomes 1. So e to the 0 just becomes 1. 1 times 2.5 becomes 2.5. If you're not super comfortable with that, you can still do that in a calculator. So second ln, e is being raised to the 0 power for x. And then now I get 1 times 2.5, so 2.5. And then next, when x equals 1, e to the first power, so second ln, and then the first power. And then it's 2.71 times 2.5, so about 6.8. And then, oops, sorry, we can set up our graph. And just do your best to graph that points as accurately as possible. So I have a point at negative 1.92, so negative 1, and then almost to 1, and then 0, 2.5, and then my next point is 1, 6.8, so we're just going to use that to kind of guide where our graph is going to go. It's not actually going to reach up there. So you can see it's still an exponential growth graph. It looks like growth. It is growth. It's still an exponential because I have a base being raised to a variable exponent. It's just in this case, the base is e. And then for b, y equals e to the negative 0.2x, we'll do the same thing. We'll graph it with a table. And then for our table, we'll use negative 1, 0, and 1. Same thing, we'll just use a calculator. So we're raising e to the negative 0.2 times x. So second ln to get the e raised to. And then I can even do like negative 0.2 times x inside the parentheses. So negative 0.2 times negative 1 for x. So that's about 1.22. And then if I raise e to the negative 0.2 times 0, well, negative 0.2 times 0 is just 0, so it's raising e to the 0 power, which is 1. But same thing, if you don't, like, if you're not super comfortable with it, just test it on the calculator, double check. So I can just rewrite this problem that's already up here. So negative 0.2 times, instead of negative 1, I'm going to change that to a 0 power. So e raised to the negative 0.2 times 0 for x is 1. And then when I input x equals 1, I can go back and just rewrite that line. So instead of e raised to the negative 0.2 times 0 for x, I'm going to change that 0 to a 1 because I'm putting 1 in for x now. So that's about 0.82. And then we can plot those points. So negative 1, 1.22, so about negative 1, and then almost like up 1 1/4, and then 0, 1, and 1.82, so between 3/4 and all the way up to 1, so about right there. So this line is pretty flat, but it's still going to be an exponential because we're raising a base e to the x power to the 0.2 times x. It's an exponential decay function. It just doesn't go up as quickly or down as quickly because we're multiplying 0.2 times like the x value or times that x variable exponent. So it's going to slow down how quickly it's decaying. And then the last example, example 4, use properties of exponents to rewrite the function in the form y equals a times 1 plus r to the t, or y equals a times 1 minus r to the t. Then find the percent of change. So this is just the exponential growth formula, and this is just the exponential decay formula. So we can use properties of exponents kind of like in reverse to manipulate these equations in that form. So I have y equals e to the negative 0.75t. So this is kind of like the last example from 6.1, where I'm going to use those exponent properties backwards. So the first thing I'm going to do is I'm going to separate the negative 0.75 from the t, using the power of a power property in reverse. So I'm going to change this to e to the negative 0.75 raised to the t power. Because the power of a power like we have here, if I wanted to simplify this back, I would multiply these exponents, negative 0.75 times t, and I would get back here. And then now e to the negative 0.75, those are both numbers. Like neither of those are like actual variables, so I can simplify that. So I can raise e to the negative 0.75, and that's about 0.724. So I can change that E to 0.4724 raised to the t, and then now we're getting really close to the decay formula. And then once you get to this step, the way you can tell like if it's growth or decay is like if this number is less than 1, it's decay. If this number is more than 1, it's growth, because if it's less than 1, we're subtracting the rate of change, and then if it's more than 1, we're adding it. So 1 plus something would be adding that rate. So in order to find the actual percent of change rate, we would have to go back and do 1 minus 0.4724, and that'll tell us the difference, and then also like, yeah, the difference, sorry. So I got 0.5276, so I can change this 0.4724 into 1 minus 0.5276. And I'm not changing the value in here. I'm just like basically finding the difference between 1 and this number. So 1 minus 0.4724 is going to tell me also what I can add to 0.4724 in order to get back to 1. And you can always double check like this number to make sure you're not changing the value. So 1 minus 0.5276 gets me back to 0.4724. So 0.5276 is going to be the percent of change. So the only other thing that the decay formula has is a 1 out in front. So if you see, like, if you don't have a coefficient out in front or a value for, or sorry, not the 1, the decay has a out in front. So if you don't have a number out in front of here naturally, it just means that the a is 1. Like if you don't see a number in front, like if a variable, it's always 1. So our a value is 1 here. And then our percent change is that r value 0.5276. And then lastly, just to change it to a decimal, we can, or sorry, to a percentage, we can move that decimal place twice to the right. So it'd be about 52.76%. And then for B, y equals 0.5 e to the 0.8 t. So we're going to kind of follow the same steps as we did over here. First, we can break apart the 0.8 t. So I'm going to rewrite it as y equals, I'm also going to pull out the 0.5 in front, and then the e to the 0.8 will go inside parentheses, and then that's going to be raised to the t power. So we're using that power of a power property in reverse. We're breaking apart this like product basically into two different factors there. So if I were to simplify this back, e to the 0.8 to the t, I would multiply 0.8 by t and get back to 0.8t. And then now e to the 0.8, same thing, like e is not a variable, it's a number. So we can simplify what's inside the parentheses now. So e raised to the 0.8 is about 2.2255. So we'll change the inside of the parentheses to 2.2255. So that 0.5 will stay on in front. E to the 0.8 changes 2.2255 to the t. And then now, because we have a number greater than 1, it's definitely growth, because we're not going to take like 1 minus r and get to 0.22 or 2.2255. So if I want to find what the actual r is, or the percent of change, I can just take 2.2255 and subtract 1, or you can just knock 1 off the whole number part. So the rate is 1.2255. So we can change this part into, so 0.5 times, I'm going to change 2.2255 to make it look exactly like the exponential growth. I'm going to change it into 1 plus 1.2255. So not changing the value, just rewriting it as 1 plus something as a sum, and then raise the t power. And then this is kind of what I was saying before about how like if you have an a value, it'll like naturally be there. If there's no number naturally there, the a value is just 1. And then now we can see what r is and what the percent of change is. So percent of change if our r is 1.2255, if I want to change that to percentage, I have to move that decimal place twice to the right. So it's about 122.55%.